Well, thank you, Emily, once again. And thank you. Many of you have joined. So I saw at least 200 people coming in. So thank you all for joining in. So there are a few questions. We will take the ones that are immediately pressing. So there's a starting out question by Rajagopal Rayavarapu. And he says, thank you for the insightful presentation, Professor Carter. My question is, in noble metals such as gold, silver, platinum, which metal has the potential to play as a photocatalyst? What is the future of these gold, silver, platinum in the area of catalysis, like these precious metals?
Well, in the example that I gave, which was in particular for the plasmonic photocatalysis, there are precisely four elements that have the activity to harvest light in this way. And they are the coinage metals, so copper, silver, and gold, and aluminum. And so obviously aluminum is the cheapest, and so it's nice to think about using aluminum. And there is actually work going on now to see whether or not, aluminum, of course, oxidizes. So there's a thin layer of alumina around it. And the question is, is it the case that the plasmonic behavior can actually go through the aluminum still? And so that's actually ongoing research that we have now with in collaboration with Naomi Hallis's group. And they are deliberately making things like core shell nanoparticles with one of those coinage metals that does the plasmonic light harvesting with, for example, titania. And so it really depends on whether or not either the electrons can transfer through, which in alumina will be a problem, or whether the actual energy, the aluminum is thin enough for it to go through. So in fact, that's part of why the focus a lot has been on copper, because copper is, of course, the cheapest. You could do copper or silver, right? Are really quite inexpensive. Gold is nice because, especially the gold is nice for experiments because simply because it's not very reactive. In the case of copper and silver, you're always wondering about oxidation, right? But a lot of this work has been done on copper and silver. And the nice thing is that what you're doing in this, so Naomi, Peter Nordlander, and I, were published a paper now about 10 years ago about this, what she dubbed the antenna reactor complex idea, which is an idea from biology for photosynthesis, but the idea being that the plasmonic particle can harvest the light, and then you have a reaction happening right next to it. And so what she had done and has done is to put smaller particles, catalyst particles, on the metal nanoparticle. So that's one way. What we proposed to her, and she did it, and this has now been working very well, is to dope at the surface a substitutional atom. And now this is a field called single atom alloys. We have a big project on that too with this same group and Charlie Sykes, who works on this. And the idea is then you could use platinum, like you mentioned, which is very expensive, as a dopant. So you don't need very much of it. So those are the kinds of ways that as long as it stays at the surface, it doesn't mess up the plasmonic light harvesting. And of course you want it at the surface to be able to do the catalysis. So that's just one example. I could talk about this all day. So we should go on to another.
Yeah, Emily, thanks. Kshetra Mohan Sahu, he asks that it's interesting to see the pulsed heating and quenching method for improvement over the Haber process. Usually high temperature favors gas solid desorption. How is it possible that while lowering temperature, ammonia desorption is favored here? How does this compare with Haber process in terms of energy and conversion efficiencies?
So, I mean, it's clear that there is not yet one of these techniques that reaches the Haber-Bosch efficiency, right? Because the Haber-Bosch efficiency has had more than 100 years to develop its efficiency. So I will say, I'll give you, I don't have the numbers for, and there may be numbers in that paper that I know that the slides are going to be posted, so you'll have a chance to look at that paper in Nature from 2022 by Liang Bing Hu. You can look it up. They may have put in there a comparison in terms of the efficiency. I would be surprised if it is terribly close because it's a lab-based experiment. I can tell you that in the case of plasmonic catalysis for ammonia synthesis, there's an example that has, if you scale industrial Haber-Bosch to the lab scale, which is not as efficient, and then you compare that lab scale to the lab scale for the plasmonic synthesis, we can get to within a factor of 4, okay? Which is quite encouraging. It's still not where it needs to be, and all of these things you need to show scale up. So, so that's the answer about efficiency. I think you asked a question about ammonia. Of course, ammonia will desorb. All of it will want to desorb at high temperature. So that's the point of any stable gaseous molecule will want to desorb at high temperature. And but of course, it's constantly hitting the surface, right? In the reactor. And so if you're at a high enough temperature where you can break the nitrogen bond, you can, not all the time, right? But some of the time that bond will break and then it'll stay on the surface and can overcome the NH, the barriers to forming NH bonds. And if you stayed at that high temperature, once you made ammonia, it would of course immediately desorb. When you come down in temperature, if you come way down in temperature, you would just have ammonia on the surface, but you want to stay at a temperature that's high enough that the ammonia will desorb because that's what you're trying to collect. So it's a balance. And the idea is, I mean, what I think is very cool about this approach is, you're using sort of the least electricity you need. It's not you're not constantly heating. So it should be more energy efficient if it remains to be seen at scale. That it all works, but I think it is very promising. And the fact that you're able to toggle between these two competing effects that need to happen at different temperatures.
Okay. Yeah, nice. So next question is by Shujan Manna. I probably know this person is a student from IIT Chennai, IIT Madras. Can you please shed some light on how only charge transfer is dictating the orientation of the molecules sitting on the metal surface? Aren't more thermodynamic factors involved? I guess I don't
I
know.
think, okay, you're
Yeah,
mixing up two things. So,
yeah, maybe this is yeah,
yeah, so it's not that it's not the orientation. It was
right.
the preferred site for CO. Actually, it's not just CO as in certain in work that we've done. Other intermediates in the CO reduction also sometimes prefer other sites. But in the case of CO, the reason that it in density functional theory, it prefers the wrong ad site in pure density functional theory. I can tell you in the so-called hybrid density functional theory that introduces some exact exchange, you can find a mixture that will bring it to the ATOP site. But it is in fact could have a long discussion about the fact that theoretically it's not an appropriate theory to use for metals fundamentally, the hybrid DFT. Anyway, but the point is, why does that happen? It happens because density functional theory, the exchange correlation functionals that exist that are good for metals, that have the right physics for treating metals, have they have an error associated with them called delocalization or self-interaction error, but it's fundamental to those exchange correlation functionals. It makes it too easy to delocalize charge, to delocalize electrons. In the case of CO, because the major bonding on copper is d pi p pi back bonding to the CO, if it becomes too easy to do that, then you can imagine, the more coppers that can do that d pi p pi back bonding, the better. And so it prefers to sit in a site where it has 3 coppers doing it rather than 1. So that's why.
Yeah. Okay, cool. Emily, just a related question with this that I had. Would you, like in the plasmonic photocatalysis part that you talked about, is there a way to distinguish heating effects from the actual plasmon effects?
Yeah, that's a really good question. And Naomi Hallis's group has worked very hard to do that. And there are papers that I think I'm a co-author on at least one of them, but there's that she's published a number of papers isolating that. Absolutely. You can isolate, you can measure the temperature of the particles, and you can then, for example, do the experiments in the dark at that temperature. And so then you can see the effect that shows what is ground state chemistry and what is excited state chemistry.
And your methods, the correlated wave function methods, it can be also applied to systems which are isolated, like clusters or cages, molecules inside cages that are reacting with charge transfer
Absolutely.
as a
Yes.
basis. Okay,
Yeah,
okay.
we have a version that Mark Martirez, when he was in my group, um, uh, worked on with me. We call capped density functional embedding theory that allows this to work for non-metallic
Oh,
systems. So,
fantastic. Yeah, we'll be
and
interested. Yeah.
so,
Okay, cool.
yeah, so it works now for semiconductors, for ionic systems, for metals, for liquids. It works for anything
Sure,
now.
sure. Okay. Mihir Kumar Jha says, out of all the electricity-driven transformation that you showed today in the presentation, which one, according to you, has the higher potential for industrial scalability?
That's a great question. Um, I mean, we know that electrolysis can be scaled. So I think that's, you know, I think there the issue is finding both, and this is something I really want to emphasize, and we are emphasizing it in other programs that we've launched in my capacity at the DOE National Lab, is that one needs to not just focus on materials discovery, but process discovery. And so I think that that in the case of electrolysis, again, thinking about, and there are people working on this, uh, would pulsing make a difference in electrolysis? Would setting up tandem processes make a difference in electrolysis? So I think electrolysis in many ways is proven, and so to work at scale. So that's one point. I think that the pulse heating and quenching is another one, which in particular is, I don't know, you're asking me to choose between my children, right?
Sure,
And
that's
that's it's not really fair. But I do think that the pulse heating and quenching could be pretty easily scaled up. And so I think that has a very bright future. And the plasmonics, there's a startup company that is getting pretty decent yields as well. So I think they all have a chance.
yeah. Okay. Raja V is asking about this one aspect that you mentioned, plasma-based synthesis. Can you explain the scope more of manufacturing materials using plasma methods? Is there particular direction which is sort of
Well, so far,
going to be
I mean,
applied?
it's quite new. I
Yeah.
mean, there are certain groups. There's a large group in Belgium, and Anna Marie Bogaerts. I'm probably not pronouncing her name right. Um, uh, has a very large group working on plasma catalysis. There's quite a bit of work that's been going on at Princeton and the Princeton Plasma Physics Lab on plasma catalysis in Bruce Kale's group and Yiguang Zhu's group and Michelle Sarrazan's group. And so it is a focus. The work that has been going on is related largely to hydrogen production, either through methane pyrolysis or dry methane reforming. The materials that form, for example, there's been work also at PPPL by Yevgeny Raitsis, his group, where the methane pyrolysis in the presence of iron catalysts can produce carbon nanotubes. So there are ways to produce various allotropes of carbon. It has not been used as much for other material synthesis, although it is used, so not plasma catalysis. Plasma, of course, is used all over the place for spray deposition, for example, of coatings on jet engines. It's used in the microelectronics industry for both etching and chemical vapor deposition. It's used in quantum materials. Both of those areas, both microelectronics and quantum plasma synthesis of materials is done. We have large efforts at Princeton Plasma Physics Lab in those areas.
Okay. Peng Jiuji is asking, in ammonia decomposition through photocatalytic process, why is the iron-doped copper appear a faster rate, that gives you a faster rate or a lower barrier than the ruthenium-doped copper catalyst?
Because the excited state, if you look at the excited state potential energy surfaces, which I didn't show, the barriers are just lower in the excited state. Why are they lower? We don't, I mean, I don't have a deeper answer than that at this point. I mean, it's a good question.
Okay. The other part, there's Lakshi Saikia. She's asking, how can we design a suitable catalyst for dinitrogen reduction, wherein the hydrogen evolution reaction can't dominate over the N2 reduction reaction? I think she's talking about competition of proton reduction versus N2 reduction.
So you're talking electrocatalytically.
Yes,
then.
electrocatalytic.
Yeah, there aren't any good nitrogen reduction catalysts yet. We've done some work on that, proposing an exotic catalyst that people are trying to make, but I don't know whether it'll ever get made. Okay. But the other, it's extremely hard, right, to reduce the N2 bond, and just like it's hard to break the N2 bond. I think that's an area that still requires a lot of research. I think that one of the areas that we've been looking at is other species to form ammonia electrocatalytically, like nitrate. And so that's actually work that we started under BP support a while ago, and are looking to understand the mechanisms associated with that using these techniques that we've been using for CO2 reduction.
Okay. Emily, last question before we sort of get your final words and thoughts. So Shujan Manna, and there is one more person, I guess, at the end. It says anonymous attendee, but both are kind of in the same ballpark of asking about CO2 reduction. So the idea being that can you change facets of copper 100 versus 111, and sort of dictate the mechanism of CO2 reduction?
Yeah, so it's really interesting. We've mapped them out and I encourage you to look at our papers on copper 111 and copper 100, and they're different intermediates. If you look at the literature on the measurements, the onset potentials are very different on those two. They sometimes produce different products, and in fact, a normal copper electrode is going to have a mixture of different facets. It's going to be polycrystalline. So you have all these things happening at once. what we've shown, and I thought it was just interesting to give as an example, is that if you specifically prepare surfaces that have certain defects, then you can also tune the chemistry, right? We saw that both experimentally and theoretically, we could explain that. And so we've done recent work that we're about to submit for publication, looking at what happens if you have defects in the surface, like vacancies in the surface. How does that change the reaction pathways, both the energetics and the selectivity? And so all of these things are things that can be played with. And as the experiments I showed show you, they can be done deliberately.
Cool. Thank you, Emily. This was wonderful. This was detailed explanation. Before I head back to Diksha and Pragati, could we hear some of the last words for everybody that you would like to give us at the end of the talk? Yeah.
Sure. So I just want to say that, I am closer to the end of my career than hopefully all of you. And I just urge you to stay with it. And no matter what, no matter what happens in your country, the work that you're doing is meaningful and incredibly important for the future of science and the future of civilization. And so I just urge you to, keep the enthusiasm. If you ever need, more enthusiasm, seek out people. Don't despair. There's been a lot of despair in our country this past year. And I think, for science in general. And so, I think, politics goes in waves, and I expect this to end at some point, and it'll be easier again. But every country, I think, probably has the possibility to go through these times. And I think it is incredibly important to make sure you have a circle of people around you that can keep your spirits lifted and be reminded of what you can contribute with your talents to making the world a better place. And you can do it through science. And I would urge you to read that opinion piece that I wrote, which is, our role in solving global challenges. I think that's the title of it, colon an opinion, because it's just my opinion. But it lists not just problems that chemists can contribute to, but also that many other scientists can contribute to, and not just in sustainability science, but in health, etc. So good luck to all of you, and thank you for being scientists and being interested in science.
Thank you, Emily.